Hi, my name is Kasra, and today I'm gonna talk about the concept named energy of graphs in algebraic graph theory. In fact, I will present our paper about steric inequality on energy of H partition of graphs. This paper was accepted in Journal of Linear and Multilinear Algebra. And during this presentation, we consider all the graphs are simple and undirected. First of all, I shortly explain the relation between graph theory and chemistry. And now you can see that we can easily turn a molecular structure into equivalent graph. There exists an interesting relation between a certain parameter of a molecule and its graph equivalent. For example, the close correspondence between the graph eigenvalues and the molecular energy. And in 1970s, energy of graphs, a Serbian chemist named Ivan Gutman defined the energy of graphs in a way that it was related to the molecular energy. Now we need to define the adjacency matrix of a graph to learn what is the energy of graphs. The adjacency matrix of a graph G is a matrix A. And for A, we have if ith vertex and jth vertex are adjacent in G, then Aij would be 1. And in otherwise, Aij would be 0. Here we see a simple example of how we can derive the adjacency matrix of a given graph. There are some properties for adjacency matrix of A. Matrix A of a given graph G. Since Vi is adjacent to Vj, then Vj is adjacent to Vi. So I is symmetric with 0 on diagonal because there are no loops in G. And it is easy to see that all eigenvalues of a symmetric matrix are real. So all eigenvalues of A are real, which are denoted by lambda I A. Now I want to define the main concept of this presentation. G is a graph with adjacency matrix A. The energy of G is equal to summation of absolute value of eigenvalues of A. Here an example of calculating the energy of K4. First, we write down its adjacency matrix, then we have to find all of its eigenvalues, which we can see it has one eigenvalue equal to 3 and 3 eigenvalue equal to -1. The only thing that remains is to sum the absolute value of eigenvalues, which would be 3 plus 3 multiple 1. So energy of K4 is 6. We need some other definitions here. Let A is an Mn matrix. Adjoint matrix, which is denoted by A star, is equal to conjugate transpose of A. In other words, A is a matrix. A star is a matrix from A star is a matrix obtained from A by taking the transpose and then taking the complex conjugate of each entry. And then A is a Hermitian matrix if and only if A is equal to A star. And then we want to define singular values. If singular values of A is the square root of ith eigenvalues of A star A. Excuse me. And we know that A star A is a matrix with all of its eigenvalues being positive, and it makes us able to take a square root of each eigenvalues. Now let G be a Hermitian matrix. It is easy to see that sigma IA is equal to absolute value of lambda IA. If A is adjacency matrix of G, it is symmetric. And all its entries are 0 or 1. So it's Hermitian. And so sigma IA is equal to absolute value of lambda IA. And so we can see that the energy of a graph is equal to summation of its singular value. Here we have another simple definition. Let be a graph. H1 to Hk be some subgraphs of G. We say that H1 to Hk is an H partition of G if both of the following holds. The union of edges of every Hi be equal to the set of edges of G, and the intersection of edges of Hi and edges of Hj be an empty set for all I and J. There is an example of edge partition here. The goal of this example is to make each edge partition into a spanning subgraph. And finally, we want to get the main theorem. Let G be a graph and H1 to Hk be an H partition of G. Then this inequality holds. Energy of G is always less than summation of energy of Hi. And the question is when does the inequality hold? When does the equality hold? And at first we want say an obvious answer. Let G be a graph and G1 to Gk be its connected components when K is more than 2. It's easy to see that G1 to Gk is an H partition, and obviously we can see that energy of G is equal to summation of energy of Gi. And now we have seen that for non-connected graph, the equality can hold. Now, you may ask these two questions. Are there any other cases of equality? What happens if the graph is connected? Again, we are going to have some definition and properties here. Unitary matrix. U is called the unitary if and only if U star is equal to U inverse. In other words, U star U equal to U star equal to identity matrix. And here is an important definition. A as semi-definite matrix, positive semi-definite matrix if and only if for all vertex X except 0 X star AX be non-negative. And yes, and A is positive semi-definite if and only if A is Hermitian matrix and all of eigenvalues of A is non-negative. And now I want to show you an important theorem which can obviously conclude the previous theorem from this one. Let A and B is our matrix from size n. Then the following holds. Summation of singular values of A plus B less than summation of singular value of A plus summation of singular value of B. And moreover, the equality holds if and only if there exists the unitary matrix such that both of UA and UB are the positive semi-definite matrix. And this claim is the main result of this presentation. Let G be a connected graph and H1 to Hk be an H partition of G. Then we have this inequality. Energy of G is strictly less than summation of energy of HI. Now it's time to prove our claim. At first, we prove our claim for K equal to, and when we have two H partition. Let G be a graph, and H and K is an H partition of G. As we have seen before, we can assume H and K are a spanning subgraph. How to make H and K is the spanning subgraph? It is easy to see that by adding other vertices of G with 0 degree to subgraph H, we will have a spanning graph H prime. And it is easy to see that energy of H is equal to energy of H prime. Now, let adjacency matrix of G, H, and K are A, B, and C respectively. We want to prove A is equal to B plus C. The edge that connected Vi to Vj in G must connected Vi to Vj in either of H or K. And this edge Eij cannot be in both of H and K. Also, if the H Eij does not exist in G, it won't exist in neither of H or K. No, it's obvious that A is equal to B plus C. No, okay. This lemma is kinda a new observation, and it's a going step in our proof. It says that all diagonal entries of BC must be equal to 0. Since H and K are H partition, they have no common edge. If Eij doesn't exist in G, it would be exist in neither of H and K. So the entries Bij and Cij are both 0. And in case that Eij exists in G, it should be in one of H or K. It cannot be in both of them. So either Bij or Cij is 0. And by all of this expression, I mean that at least one of Bij and Cij should be 0. And we know that C is symmetric matrix space. So Cij equal to Cji. Hence, Bij, Cij is 0 for all j between 1 to n. So Bci, as you can see, ith diagonal entry of BC is 0 because all of Bij, Cji is equal to 0. And I think this lemma can be used also in solving other problem about H partition. An immediate result is that the summation of all diagonals entry of BC, which defined as trace of BC, is equal to 0. Now, by contradiction, assume that energy of G is equal to energy of K and energy of H. By definition, we have summation of singular value of A is equal to summation of singular value of B plus C is equal to summation of singular value B plus summation of singular value of C. By equality condition of the theorem about singular value, there should exist an unitary matrix U such that UB and UC are both positive semi-definite. And actually, multiplying B and UB and UC was a random idea that we used to prove the claim. We define T as multiple of UR and UB. From linear algebra, we know that eigenvalues of the multiple of two positive semi-definite matrices are non-negative. And since UR and UB are positive semi-definite, we have all of eigenvalue of T are non-negative. We know that U B is positive semi-definite. So UB is Hermitian, then UB is equal to UB star. Hence, we can write T is equal to B star, U star, UC. And we know that B is symmetric. Then we have T is equal to B, U star, U. And we know that U is unitary. So U star U is equal to identity and T is equal to BC. We conclude that the trace of T should be equal to trace of BC, which we have proved that is equal to 0. First, we know that the trace of a matrix is equal to summation of its eigenvalues. The trace of T is 0. So summation of its eigenvalues is equal to 0. And second, all of the eigenvalues of T are non-negative. Now we have some non-negative real number, which their summation is 0. So each of this number should be 0. Excuse me. It means that all eigenvalue of T are 0. Therefore, its characteristic polynomial is x to the power n. And we know that each matrix is the root of its characteristic polynomial. So T to power of n is equal to 0. In other words, it's nilpotent. Here we have a lemma that we won't prove. No nilpotent matrix except the 0 matrix is the product of two non-negative matrices. And we know that T is nilpotent. Also, T is product of UB and UC. And we know that UB and UC are positive semi-definite. So by the above lemma, T must be 0. Therefore, BC is 0. As we assume G is connected. Now, we want to prove BC is not equal to 0. As we assume G is connected. So there must exist a vertex Vi that is adjacent to a vertex Vj in H and also is adjacent to a vertex Vk in K. So Bij and Cik are both 1. So Bjk is more than 0 and non-negative. So BC is yes, and BC is not equal to 0. And we have a contradiction and we proved the main claim for K equal to. Now we are gonna prove that for K greater than 2. Let G be a connected graph and H1 to Hk be an H partition of G. Let G be a graph. Let Gh be a graph G without H of H1. In other words, G is union of H2 to Hk. H1 and G1 is an H partition. So energy of G less than energy of H1 plus energy of G1. And also H2 to Hk is an H partition of G1. So energy of G1 is less than summation of energy of H2 to Hk. And now it is easy to see that energy of G is strictly less than summation of energy of Hi. And what if G is non-connected? It is easy to see that let G be a graph and C1 to Cm are its connected component. And we have H1 to Hk is an H partition of G such that energy of G is equal to summation of energy of Hi. It is easy to see that for I between 1 to K, Hi is union of a number of some connected components. And we have another question. Let G be a graph and V1 to Vk be a vertex partition of H. Also define GI induced subgraph on VI for all I between 1 to K. Then the following holds. Energy of G more than summation of energy of GI. And we have one question. When does the equality holds? Thank you.
All right, thank you so much, Kasra. Everyone, please join me for a round of applause by giving a clap reaction in Zoom. Does anyone?
Thank you.
Thank you so much, Kasra, for the call.
Thank
Does
you,
anyone
everyone.
have any question?
So for the last question you asked, do you have any intuition? When would that work actually? When do you have equality? You're yeah.
Yes, we search in any equality condition and we find some graph that equality holds, but we don't have any good condition. And yes,
No,
I think
no.
We can't find a good, sufficient, and necessary condition for this question. We tried to find this condition.
Yeah, I guess it's not easy, no. Yes, thanks. Nice.
Please repeat to us your last sentence.
Ooh, no, I'm just saying that it must be quite difficult, yes, to find a good, sufficient, and necessary condition. But yeah, thanks. It was nice.
Okay, thanks, Thomas.
Thank you, everyone.
Have any question? Okay, if not, please again join me for giving Kasra a round of applause.